Hi, geometry friends. We're in chapter 12. We're looking at the last section of the chapter that we're going to cover, 12.8, congruent and similar solids. So we have a few vocabulary words, similar solids and congruent solids. Probably the best way to look at this would be for me to make this a little larger so we can see. So here we have a diagram of similar solids, and notice that the ratio of corresponding sides in terms of the linear measure, that's important. So here I have a linear measure. What does that mean when I say linear? It means that when I talk about the height, I don't say the height would be 5 inches squared. I say it'll be 5 inches. Notice that's linear, or the height here might be 12 inches. Anything that's linear, it's going to have a ratio, a common ratio between it and the corresponding part of the other object if you have a similar solid. So as you notice here, the height of one related to the height of two is going to be the same as the radius of one as related to the radius of two. So I think of similar solids as basically an enlargement in every possible way, and that enlargement, in a sense, has a common ratio. When we talk about congruent solids, you can look at them the same way. You can say there's a relationship between the height of one and the height of the other, and the slant height of one and the slant height of the other, but that ratio has to be 1 to 1. Basically, it has to be the same exact size, which I think you understand. Let's go ahead and see if we can identify them in the next example. So this example gives us an opportunity to determine whether each pair of solids is similar, congruent, or neither. And if the solids are similar, state the scale factor. And that's what I was calling the common ratio. So we'll call it the scale factor from here on out. So remember, we realize that any linear side has to have the same ratio to the a linear side of the common figure. So watch this. So I know that these are both heights. So 4 is to 6 as, let's see, question mark, as 8, this length, this linear length is to this linear length, 12. So as 8 is to 12. So when I look at that, 4 is to 6 is 8 is to 12. This looks like it's true. I can check by multiplying crossways. So 48 and 48, that's the same? Yes. These two prisms, or pyramids rather, are absolutely similar. And so with the knowledge of the similarity reach, we know that they're similar, not congruent, and not neither, but we need to also find the scale factor. And so the scale factor is 4 to 6 reduced down to 2 to 3. And so we can write that this is the scale factor, 2 to 3. Let's take a look at some, wow, too far. Let's take a look at some regular prisms and see if we have that same situation. So we can look at 1.7 to 3 and 3.4 to 6.2 and 1.5 to 2.5. And already I get the sense that this isn't the case, because if I look at 1.7, 1.7 doubled is 3.4, and 3 doubled would be 6 and not 6.2. So that indicates to me that the ratios here aren't the same. And if the ratios aren't the same here, then we do not have a similar similar solids here. So without the similar solids, I'm going to write that these aren't equal, and these don't appear to be equal either, but I'm going to hold off on that. Doesn't matter. The fact that I find one ratio that doesn't correspond to what we need is enough. So I'm going to put neither here. And clearly they're not congruent, not just because of me eyeballing it, but if you look at the sides, they're not the same length. All right. So we have a theorem that we're coming up with, and this theorem has to do with the idea of area and volume based on the scale factor of similar solids. So here's what we know. If you have two solids that have a scale factor of a to b, some scale factor a to b, then the surface areas have a ratio of a squared to b squared, and their volumes have a ratio of a cubed to b cubed, okay? So if we had this earlier, one of our solids or pair of solids had a ratio of 2 to 3, well then here we could also know that the ratio of their surface areas would be 4 to 9, and then their ratios of their volumes would be 8 to 27, as 2 squared is 4 and 2 to the third power is 8, and similarly 3 squared is 9 and 3 to the third power is 27. All right. Okay, let's look at this example here. We've got two similar cones And two similar cones have a radii of 10 millimeters and 15 millimeters. What is the ratio of the surface area of the small cone to the surface area of the large cone? Well, I like this problem because it gives us a great opportunity to see what we can do. We're talking about the radii, so we're talking about the same side. 10 to 15 would be the scale factor. And so when I reduce that, I get 2 to 3. Very similar or common scale factor that we've been working with. So now that I've got 2 to 3, then I know that the surface area would be, I'll write it like this, 2 to 3. That's the linear. When I'm dealing with the area, it's going to be 4 to 9. You can look up here and see that that's what we had last time, or you can recognize that we're just saying 2 squared, 2, 3 squared is how we get those values. In example 3, we're going to use similar solids to find the unknown information. So the containers at the right are similar cylinders. Find the height h of the smaller cylinder. So they've given us the volume. They've told us that we have similar cylinders. So we already know that, let's say the scale factor is A to B, then we know that the surface area ratio will be a squared to b squared, and the volume will be a cubed to b cubed. And so now that I have that information, it will be really good if I could find the scale factor by simply taking the cube root of the volume, right? Does that make sense? If I can go back in a way and figure out what thing cubed got me to 270 and what thing cubed got me to 640. So A, in a sense, is equal to 270 cube root, and B is equal to the cube root of 640. So check out how I'm breaking this down. I took 270, wrote it as, 27 times 10, and 640 is written as 64 times 10. The reason why I broke it down like that is because I can take the cube root of 27, which is 3, because 3 to the third power is 27, and I can take the cube root of 64, which is 4. 4 to the third power is 64. But the 10 and the 10, alas, need to stay indoors. So does this mean that h is equal to this number? No, no, no. Remember, this just gives us the basis in order for us to figure out the scale factor. So a to b is my scale factor. So 3 root 3, the third root of 10 to 4, the third root of 10 is my scale factor. Let me write that as a fraction. Let me write that as a fraction. So I've got this at the top, and let's say this thing at the bottom. And you know what you want to do. You want to cancel it out because these guys are the same thing, so that doesn't matter. So in a way, our scale factor is 3 to 4. Not in a way, our scale factor is 3 to 4, all right? So if our scale factor, our linear scale factor is 3 to 4, then when I'm looking for h, I have to, let me get myself a little bit of space. I'll say 3 is to 4 as h is to 10. I can cross multiply and I get that 4 times h equals 30. Divide both sides by 4 and I get 7.5, I believe. 4 goes into 30, 28, yep, 2 over 7.5 is my final answer. So my value, h would be 7.5 inches as my final answer, all right? I think actually that's our last problem. I hope this made sense. This is a really powerful, powerful theorem. And I look forward to talking to you guys soon. For all intents and purposes, we've done chapter 12 as far as I want to get into it. And we will be looking at chapter 13 the next time we see each other. I need you guys to take it easy. I look forward to talking to you soon. Bye-bye.